Stress is developed when a force is distributed over an area. Stress has the same units as pressure. So as we know, as a result of external loads, and thus internal stresses are developed within structural members. These stresses can be resolved to be acting perpendicular to the cross-section and parallel to the cross-section. A stress that acts perpendicular to a cross-section is known as normal stress. Normal means perpendicular to, and it is denoted by a specific Greek letter, lowercase sigma. Normal stress arises as a result of an internal normal force. On the other hand, a stress that acts parallel to or tangent to a cross-section is known as shear stress, denoted by another Greek letter, lowercase tau. Shear stress arises as a result of an internal shear force, which acts parallel or tangent to a cross-sectional area. For example, the bar shown here is subjected to an external normal force P, and thus an internal normal force N equals P. Since a normal force, as we learned in statics, can be either tensile, meaning it's pulling on the member, or it can be compressive, pushing on the member, feeling contraction. A normal stress then can either be tensile or compressive, as shown. So here's a state of tension, pulling on the bar. Compression is being illustrated on the right, pushing or pressing on the member. Average normal stress is therefore defined as follows. We denote it, as we said, by lowercase sigma, that equals N over A, where uppercase N is the resultant internal normal force, typically measured in newtons or pounds, which acts through the centroid of the cross-sectional area. Uppercase A on the denominator here is the cross-sectional area of the member where normal stress is being determined. And then sigma is average normal stress acting on the cross-sectional area. So since we have N in the SI system in units of Newton, A in the SI system in units of meter squared, typical units for sigma would therefore be Newton per meter squared. We're going to call that a Pascal, named after Blaise Pascal, who we did mention in the first part of chapter 1. So uppercase P, lowercase a represents 1 Pascal, which is 1 Newton per square meter. Or we can represent it in the US customary system with common units of pound per square inch, which we often write as PSI. So as mentioned, shear stress corresponds to a shear force acting on a cross-sectional area. Consider this example, in which force F acts downward on this top block. If the force becomes large enough, the top block may deform and fail or fracture along 2 planes. Okay, so those 2 planes would be within this member, within this block here, 1 plane here, okay, back there, and 1 plane there. So you can imagine this little segment, this middle segment, basically fracturing at those 2 planes, okay? We're looking at a free body diagram of that segment. So the FBD of the middle segment shown here shows that the shear force V, this force on the face in the back and this force on this front face, each of these equals F over 2, acting upward on each plane, opposite to the direction of F, so that the segment is in equilibrium. So we have F over 2 because we have 2 of these shear planes and thus 2 shear forces V. So therefore V would equal F over 2 from equilibrium analysis. Average shear stress is therefore defined as follows, where we have Greek letter lowercase tau representing shear stress equals V over A, where V is the resultant internal shear force, typically measured in newtons or pounds. Uppercase A, just as we saw in the equation for sigma, equals cross-sectional area of the member where shear stress is being determined. And tau is the average shear stress acting on the cross-sectional area, which would often have units of Pascal, a Newton per square meter, or PSI, pound per square inch, or possibly other common units like kilopascal, megapascal, PSF, pound per square foot, or KSI, kip per square inch. Let's say we have a little volume element, a little differential element. We sometimes study these in this class. And let's say we zoom in on it. So this top face, okay, corresponds to this top face here where V is being applied. And since we have a shear force V, we're going to have a shear stress tau in that same direction. So when a cross section is subjected to a shear force V as shown, a shear stress tau arises on the face over which V acts, which is the top face. However, there are 3 other shear stresses that act on 3 other faces of a differential volume element as shown in this diagram on the right. These 4 in total, 4 shear stresses, must be present in this manner to ensure translational and rotational equilibrium of the body. This principle is referred to as the complementary property of shear, and it does become very important in future chapters. To have equilibrium of forces, we need to have a shear stress tau on this bottom face in the opposite direction to that one. But if we only had those 2 on the top face and bottom face, what would be happening to this element? This element would be rotating, but that does not satisfy equilibrium. In equilibrium, we cannot have that type of rotation, which means on the other 2 faces, we have a shear stress tau on the right going upward, shear stress tau on the left going downward, such that the clockwise tendency to rotate clockwise is counteracted by these 2 shear stress vectors because they counteract that by having a tendency to rotate the element counterclockwise. So this is, again, a unique property of shear forces and shear stresses, the complementary property of shear. As a final note regarding shear stress, keep in mind that depending on how a structural member is connected to pin connections, the pin may be subjected to single shear or double shear as shown below. So here we have an example of single shear, the schematic diagram, and then one of double shear. So you can imagine this pin here that goes through two boards or two members of some sort, and we're pulling on this board to the right, pulling on this board to the left. There is a plane here within the pin, inside the pin, that's feeling a shear force and thus a shear stress. So in green here is the shear plane for this state or scenario of single shear. Now if we had three boards that were basically stacked on top of one another with a pin going through them, and have one board with a force to the left, this board with a force to the right, and this board with a force to the left, we could potentially have failure along two shear planes, okay, shear failure along two planes, cross-sectional planes within this pin. This is a state of double shear, two shear planes which are shown here in green.